Hi guys, in the last video when we were talking about my DIY current sensor, I have promised you that we are taking an in-depth look into analog metering because it requires some tricks to get correct readings. So you should really know when you make your DIY power projects, when you try to measure voltages, how you have to do this correctly. Otherwise your measurements will be all over the place and they might not have anything to do with reality. So what I have here is a sort of battery monitoring setup. I have current measurement, I have voltage measurement of a battery here, and I have a display and a small microcontroller. So let's go straight into this, take a look. We will also talk a little bit about programming of this situation, and don't worry, don't be scared of this, it's not as bad as it sounds. Just to give you a short overview what I have here on the bench. So I have here our setup, we will look in detail into this anyway. I have my multimeter for measuring voltages, and on the bench here on the up I have two power supplies. One will be there to provide our supply voltage, the VCC, and the other power supply which is off for the time, and this has a reason. This one is providing just our current, so it's going straight through the current sensor here, a short, but we can then just adjust our amperage there. And this is all what we need to simulate a simple battery monitor. We have our microcontroller. This is an Arduino Nano, a knockoff board, just a few bucks of investment for something like this. It is put on an adapter board which is only give us screw terminals for every pin. Then I have a LCD display. I have my current sensor here, and then one single LFP battery cell. So let's see what the battery is measuring. We have 3.308 volts there. This is just simulating a battery. I can of course directly connect one cell into my analog to digital converter here on the microcontroller, because this is a 5 volt microcontroller, so 3.3 volt is possible to connect directly. If you of course connect a battery system which has a high voltage, then you can only read this out via a voltage divider. Let's also measure the reference voltage now. The reference voltage is this pin here, and it gives us 1.529 volts. So let's initially look at how an analog to digital converter is working. Analog to digital converters will take an analog signal, a voltage. It must be somewhere in the range between 0 volts and your maximum voltage, VCC. And then it depends what sort of digital converter it is, what sort of resolution it has. So if it is, for example, a 10-bit ADC, like here on the small Arduino Nano, 10 bits means we have a resolution of 1024 numbers which we can compare to the analog voltage signal. So if you look at this, let's say we have a voltage here of 3.2 volts, like for example the battery there, which we will have in our circuit. If we have our nominal 5 volt VCC, then this will equal somewhere to a digital value of maybe somewhere around 620. So now what happens if the VCC is not our 5 volts, it is reducing to, let's say, 4.6 volts. So this will just compress the area for our 1024 numbers to a smaller band, let's say The voltage input will still remain the same, but now the 3.2 volts will be closer to the 4.6 volts. So the result of the number will be a different one. And now maybe it will be somewhere around 700. So the voltage signal did not change at all, but because our supply voltage of the ADC, the VCC, was changed, the number which is resulting is completely different. What is the reference voltage? So usually it will derive from the main rail, typically 5 volts or 3.3 volts. And those main power rails, they usually under high load, under stress of many different peripheral components. So the voltage can vary there, so it can fluctuate a little bit. A reference voltage source should be I call it here a virgin voltage source. So you generate that voltage rail for the only single purpose of being reference voltage. There is no load on that voltage source, and then making a high impedance measurement on that rail, so there is no way that that voltage would start being unstable due to load. So we can assume that the voltage source, the reference voltage, is always correct. This is similar like you would take your multimeter, make a measurement. You also assume that what your multimeter tells you is something what you can trust. We have now our 1.5 volts reference voltage. We know this value will never change. That's an assumption, as we already said before. So if we do now a reading and we say our nominal VCC is 5 volts, for example, then we know those 1.5 volts will correspond to a certain number on our converter here. And now when we make a reading of the 1.5 volt and our result is a different number, we can just calculate the difference between the nominal ref number in a digital value to the actual. And this difference is then our correction factor, and with this factor we can then always calculate the actual VCC on the ADC. Yeah, that might have sounded complicated, but it's nothing else than, you don't know how you look like if somebody else doesn't tell you, or if you don't have a mirror, right? Voltage reference source is nothing else than a third party which is telling the ADC in which state it is at the moment of the measurement. How is the microcontroller and the peripherals connected here? On the microcontroller I have here my analog pins. So this is called the A0 pin. The A0 pin I'm using to read out the current sensor. The next one, A1, is my reference voltage coming also from the current sensor. Then the next A2, this is the plus from my battery cell here. And then the other ones, this is just for the display. Here on the current sensor, these two crocodile clips are going to this power supply, which will supply the current, and the other power supply is just providing our supply voltage. We are starting now our demonstration with 5 volts on the supply. This is exactly our nominal voltage. What do we see on the display? On the display I have following values. In line 1, this is the sensor readout. First number is the digital number, which is read directly from the analog to digital converter. The second one is calculating the voltage of that readout. In the second line, same thing, this is the reference voltage, digital number, then the calculated voltage. Then I have next line is corrected VCC. So this is calculating the difference between our nominal VCC voltage and what is actually calculated out of reference voltage. And then in the fourth lane is the current. These extra numbers here on the up, this is the raw data battery voltage, and the last number is the calculated battery voltage corrected by the reference voltage. This would be the sketch here, the program which is running on the microcontroller. Yeah, don't worry, you don't need to be a programmer nor you need to be a mathematician. It's a quite short sketch, and what I'm telling you will just make you better understand what you see on the display. Here are a few definitions which we have to make on the beginning, like which pin is responsible for what, and what is our nominal voltage, etc. Right? So we saw already on the microcontroller breakout board there. So the pin A0 we are using for the sensor readout, A1 for the VREF, A2 for the battery voltage. Then we define the supply voltage VCC of our system is nominally 5.0 volts. We have a ADC, which is a 10-bit ADC, so the maximum count there is 1024. If you have another ADC, let's say a 16-bit, the maximum count would be then 65,536, for example. And then the sensor conversion factor, that is how much millivolt will be produced on the sensor for 1 amp, for example. So in this case, the 100 amp chip is rated to output 20 millivolt per 1 amp. And then I have a multimeter VREF value, so that's nothing else than what did I measure with my multimeter at the VREF output, so that's 1.52 volts, and this will make then every reading equal if you make it by the multimeter or which is shown on the display. Should all then show a similar value, so it's a calibration that everything is showing the same thing. And then comes the variables which are used in the sketch. So we have variables for the raw data, then what we are calculating to be voltage, and then correction values, the current, etc. Here is the part which is run by the microcontroller only one time when it is starting up, and we have some setups here which is required, like telling the microcontroller that the pins are input pins, so we are reading something there. And then important thing is, at the startup we want to let the microcontroller read the sensor pin one time. This should happen, as I showed you before, when there is no current flowing yet, so that the microcontroller can store the initial 0 amperage value, right? Which is very important because this will then give the reference for the current calculation. And that's already everything what needs to be done in the setup. Yeah, this is now the so-called loop. So the loop is repeated now by the microcontroller again and again and again. If you don't delay the loop, then it will happen very, very quickly. But yeah, at the end of the loop I have a small delay of 2 seconds that we can follow the display also. So in the loop we are making our readings. We read the current sensor, we read the reference voltage, and then the battery voltage. And then we do calculations. They are not very complicated. So the first set of calculations are how do you calculate voltages out of raw data. And that's easy. It's just the supply voltage VCC divided by the ADC bits, which we set in this case 1024, and multiplied again by the raw reading, and this is giving then a voltage. This voltage is not corrected. It will vary if the VCC changes. How do we correct the VCC? This is done by the reference voltage. So here also a very simple formula. We have our multimeter Vref value, which we measure, the 1.52 volts, divided by the V reference voltage, which we have read, and this times the nominal VCC. This is giving then a VCC, a new one, so that one which is then actually really there. Then comes the calculation for the current. Also we have the sensor reading in voltage here already, minus now this 0 amperage voltage level, and this difference divided by the sensor conversion factor, which is this 20 millivolts per amp, gives us the current. Okay, and the last is then a corrected battery voltage. So for this we need to have a reference voltage readout and the battery voltage readout. So the formula here is the multimeter reference value divided by the reference voltage we measured. So this gives a difference, and this is then multiplied by the battery voltage. The rest of the commands is only there to show us the results and the data on the display. I will restart the microcontroller now, the sketch, adding some current, and I'm going to set 5 amps here. And as you can see, our readouts, they all quite nominal. Voltage at the sensor is now 2.6. 2.5 was our zero current voltage. We have 100 millivolts more now, and this equals exactly to 5 amps. Reference voltage still the same, battery voltage, everything of course the same, and we have a current readout so of 5 amps around here. Now I'm going to change the supply voltage. Let's simulate a drop in voltage to around 4.8 volts VCC. How do our readings look now? So our sensor is still showing the same 2.6 volts. The reference voltage is now 1.57 volts, which is different. Battery voltage says now 3.42 volts. The current is still the same at 5 amps, around 5 amps. And now you can see that because of our reference voltage source, we saw that the reference voltage is now actually higher than the nominal, than it should be. And from this now, without measuring our VCC directly, because we can't do that, we have calculated a new VCC of 4.83 volts. And by taking that new VCC, we can calculate the correct voltage on the battery, which is still then 3.3 volts. I will now reduce the VCC further. So the power supply is showing 4.47, and you can still see there's no change on the voltage on the current sensor, and this is because the current sensor is on the same supply voltage, and the error is the same there as on the analog to digital converter. So as long the analog to digital converter and the current sensor are supplied by the same voltage source, they will have the same error, so at the end the result will stay correct the same way. But we can again see here the reference voltage measurement is completely different. Battery voltage already says that we have 3.67, but we have calculated our new VCC here, which is 4.5 volts now, and the battery voltage is still 3.3 volts. And this is very important when you do analog measurements, that those voltages, that those readouts which stay constant and you need to measure directly with the analog digital converter, there you need a voltage reference correction, otherwise you will not have correct readings there. You can find a GitHub link in the video description, so you can download this or look at it if you want. Yeah, that is it. That's the secret about analog metering. Whenever you have a sensor which is providing constant output, so it is not a subject of a fluctuating supply voltage, then you need to have a reference voltage source to correct the metering which is done by the analog to digital converter. If in the case like here the current sensor, the ACS758 chip, which is providing its output signal also in a relation to its supply voltage, and this is behaving just exactly in the way like the ADC is behaving, then everything stays the same. So there you don't need a reference voltage correction. Yeah, sounds easy enough, right? I hope I could help you out if you have been asking this question by yourself, because I know it can be quite frustrating if you try to set up something like this by yourself and you just cannot get the right numbers out of whatever you do. Okay, so thank you for watching this video. I hope you found it interesting. Please like the video, comment, as always, subscribe to the channel, and I see you next time.